Hello, I'm Hwang from Dongguk University TTM Lab. The paper I will review prescriptive technology intelligence for technology opportunity discovery on LLM-based automated framework for narrating promising technology concept. Here is the bibliographic information of the paper. The paper was registered in the Technovation in 2026. The keyword are as follows. Table of context is organized to match the structure of the paper. Technology opportunity discovery is the systematic process of identifying how new knowledge can serve existing problems. Early theory research relied on effort-driven methods which struggled with cognitive limits and subjective biases. This led to data-driven technology intelligence, which spans three levels: descriptive, predictive, and prescriptive. Most existing research remains at the descriptive or predictive level. Current theory methods split into 2D mapping approaches, which project data onto a low-dimensional plane, and graph-based approaches, which capture relational structure. 2D mapping has recently reached the prescriptive level. Graph-based approaches remain predictive, only identifying links without turning them into actionable solutions. This paper proposes an LLM-based framework to cross that gap. Table 1. Classify prior research by methodological approach and intelligence level. Graph-based approaches have reached the descriptive and predictive levels, but not the prescriptive one, which is the gap this study addresses. 2D mapping at the descriptive level converts data into visual map, but stays tied to historical patterns. At the predictive level, it identifies vacancies only as coordinates without explaining how to realize them. Web-based approaches trace citation network descriptively and predict new links using GNN and GCN, but the output remains of abstract scores or links rather than concrete directions. LLMs now enable building knowledge graph directly from retained knowledge, improving extraction, accuracy, and generalization. Graph-to-text research generates readable text from graph structures, advancing from template-based system to neural model trained on benchmark dataset, with certain fine-tuned model achieve state-of-the-art research. This paper combines both capabilities. The framework consists of 5 steps shown in Figure 1. Graph construction has 4 steps. First, each document is partitioned into semantic block based on 8 categories: background, problem, purpose, method, research, conclusion, implication, and contribution. Second, key entities are extracted based on 5 types: algorithm, method, text, application, and other. Third, an LLM determines relation type and direction between entities, producing a directed graph. Fourth, everything is integrated and cleaned to complete the base technology knowledge graph. The base technology knowledge graph only encodes relationship already stated in the documents. Entities are embedded using RGCN, and this merge scores the possibility or relationship. A feature vector combining embedding topological and node-level information feeds an ensemble model that first predicts whether a link exists, then classifies its relation type. The resulting relationship point to technological convergence and a tape application not yet visible in the data. Community detection group closely related entities in the base technology knowledge graph into distinct technology themes. Since these themes rely on established relationships on expanded technology knowledge graph is built by integrating the newly predicted relationship, adding forward-looking structure. Generative concept or brief narrative without quantitative specification. So traditional multi-criteria methods are difficult to apply and don't scale well to a large pool of concepts. The paper instead uses an LLM as a judge approach for constant, scalable evaluation. Each concept is scored against 5 criteria. A panel of 5 different LLMs rate every concept on a 5-point scale per criterion, and the scores are aggregated to select the final promising concept. A case study targets the AI field. Your IPS proceeding from 2022 to 2025 across our highlight and poster sections were used researching in a final dataset of 17,006 research abstracts. A custom semantic block schema and entity type set were designed for the AI domain. Base technology knowledge graph construction used an LLM-based incremental construction model applying confidence threshold of 0.8 for entities and 0.38 for relations. The resulting-based technology knowledge graph contains 3,136 entities across 5 entity type and 4,498 relations across 42 relation types. The relation prediction model was trained with a 2-layer architecture and 128-dimensional embeddings. Link instance prediction except 0.9633 occurs and 0.9639 F1. Relation type classification except 0.8465 occurs and 0.8441 F1. Selecting the probability threshold involves a trade-off between coverage and precision. Raising the threshold from 0.85 to 0.90 fit, predicted relation from 1,341 to 570. A threshold of 0.85 was chosen, yielding 1,341 new relationships. The community detection resolution parameter also involves a trade-off between community size and semantic coherence. It was calibrated against a reference benchmark dataset and a resolution of 8 produced communities averaging 20.23 nodes, judged an appropriate size. This yielded 155 technology themes from the base technology knowledge graph. Integrating these themes with the 1,341 predicted relationship produces the expanded technology knowledge graph, increasing total relation from 4,498 to 5,839, about 29.8% increase. One of subgraph centered on each themes. Entities were extracted from the expanded technology knowledge graph, producing 155 expanded themes subgraph. Newly added entities and systematically important entities were visually distinguished. Each subgraph was converted into text using a fine-tuned graph-to-text model, then refined for clarity, grammar, and readability to produce the final emerging technology concepts. 3 example concepts cover multimodal visual reinforcement learning, safety, standard compliance, and node saliency. Five validative LLMs serve as the choosing panel, choosing their ability to make nuanced multi-criteria judgment on natural language descriptions. Scores are aggregated into a final rating for concept. The multimodal visual RL concept scored highest at 4.32. The safety compliance concept scored 4.2, and the node saliency concept scored lowest at 4.04. The main contribution is advancing graph-based technology intelligence on the prescriptive level by predicting new relations and narrating them into readable concepts. 2D mapping and graph-based approaches are framed as complementary. One identifies where opportunity exists, the other specifies how to realize them. The methodological novelty lies in combining relation prediction and community detection as input to the graph-to-text model. Constraining the model to the input graph structure control hallucination risk. Sim granularity can be tuned to strategic needs, and the framework is well suited to identify novel combination of established technologies. Though demonstrated in AI, the pipeline is domain agnostic and can extend to other fields by adaptive the schema. The framework reduces R&D managers' cognitive burden by translating graph structure into readable concept and reduce manual review costs through automated evaluation. Agreement among the judge model was statistically significant, but this does not equate to ground truth, so human expert validation is still needed for final decisions. This study presents an LLM-based automated framework for generating narrative technology concept through a graph-based approach, constructing a technology knowledge graph, predicting new relations, detecting technology themes, and converting them into concept. It is the first to bridge predictive graph output to prescriptive technology intelligence, enabling more efficient screening of high potential ideas. Limitations include reliance on qualitative LLM judgment brief rather than very elaborated concept and analysis confined to a single conference. Thank you. That concludes my review.